Right, hello. This is revision for chemistry paper 1. This is for everybody, whether you're doing higher or foundation. When we get to the parts to do with just higher, then I will mention that. There are 4 parts to the revision, so there'll be 4 short videos. And if you learn all the facts on here, then this will really boost your marks. So if you want to create this mind map as we go along, you can just pause the video, but if not, just listen to the facts and make sure you learn them. So first of all, let's start off by going over to the top right hand corner, and you can see we've got atoms, elements and compounds. Okay, so if we look at atoms and elements first of all, atoms are just the basic elements. It's just one particle, and if I put them together I end up making compounds. So I can make CO2 for instance. If they ask you how many elements are on the periodic table, there's just over 100. We don't give an exact number as there are still some being discovered now. Compounds, 2 or more elements joined together, and we have a formula. So you've got CO2, which is carbon dioxide, H2O is water, H2SO4 is sulfuric acid. HCl is hydrochloric acid, and worth knowing those. Please be careful to make sure you very clearly write whether it's a capital letter or a capital letter and a lowercase letter, like up here on calcium, because that is one chemical. And if you also make sure that if you are putting a little number 2 by the side to show it's 2 oxygens, that you really make sure it's subscript and otherwise, if you make it too big, you won't get the mark. How are compounds separated? Well, they can be separated through chemical reactions or electrolysis, and we'll look at those in later videos. So let's have a look then at some basic separation techniques. And you should be able to describe all of these techniques. Now, if you've just got a mixture, that is where you've got 2 or more elements in together, and they are not chemically joined together. You can easily separate them. So, for instance, seawater is made of water, salt and sand, and you could separate all of those by filtering out the sand and evaporating the water. Okay, here are some other separation techniques you should know about. Filtration, straightforward, use a piece of filter paper in a funnel and it takes away the soluble solids and the insoluble solids from each other. So anything that doesn't dissolve will end up being left in the filter paper, and then you will have the filtrate in the beaker. We've then got, if I look at the 2 green ones together, you've got simple distillation and fractional distillation. Now you probably will have heard of fractional distillation when in paper 2, when you look at separating out crude oil. And we'll probably come back to that one in a bit more detail then. But in terms of simple distillation, it's quite straightforward in terms of if I put a water sample into a round bottom flask, so ink, or it could ink water, or it could be Coca-Cola, anything that's got water and something else dissolved in it. We can then use the boiling point of water, which we know is 100 degrees, to heat up the water, evaporate out the water from the sample, and then when it evaporates here, we then use this thing called a Liebig condenser, which runs cold water around the outside so that the steam inside condenses down back into water because it's cold there, and then we can collect the pure water in the beaker. This is a required practical, and it may well ask you about hazards, and hot equipment is probably the biggest hazard for this one. Crystallisation, we use this again in a later video when we look at making copper sulfate crystals. So it's all about heating up and removing the water from the solution, but then leaving the crystals to cool down. If they cool down quickly, you make small crystals. If they cool down slowly, you make large crystals. Again, we've got another required practical here for chromatography. It's mentioned in paper 1 as a separating technique, but actually is a required practical in paper 2. So if we have a sample, 3 samples that we know, so A moves the soluble part to that distance on the paper, B moves the soluble distance to that distance on the paper, and C moves the particles to that distance, then if we look at X, X has got a green, a red and a blue, and if I match them up, I can tell you that that black ink is made up of A, B and C. We say that the paper is stationary because it doesn't move anywhere, and we say that the solvent, which is the water, which is dragged up the chromatography paper, is the mobile phase. We use a pencil line at the bottom, and we make sure the bottom of the chromatography paper is just dipped into the water because we don't want to submerge it, because we want the water to be dragged up to carry out the solutes up the chromatography paper. The next part of the topic is looking at the scientific models and how we actually developed and found out about the atoms. So the main people you need to know about are J.J. Thomson came up with the plum pudding model and said that he thought all the positive and negative particles were in the nucleus. Then Geiger and Marsden, along with Rutherford, came up with the gold leaf experiment, where they fired particles expecting them all to go through the gold leaf, but some deflected off. So they said actually the negatives must be on the outside of the nucleus, and that's where they came up with the nuclear model. Then we had Niels Bohr, who I always think of him as Boring Bohr, because he discovered electrons orbiting the nucleus. And if you just think about orbiting the nucleus, it's quite boring watching them going round and round. And then lastly, James Chadwick. I always think about Mr. Chadwick at school because he's in charge of behaviour. So he's not positive, he's not negative, he's neutral. He discovered the neutron. Okay, so James Chadwick discovered the neutron. However, we need to make sure we can describe the particles, and we can say what charge each part of an atom has. So, for instance, first of all, an atom is only about 0.1 nanometers in radius, okay? So, in standard form, that's 1 times 10 to the minus 10. If you were asked to draw a particle, you obviously need to know that the protons and neutrons are in the nucleus and the electrons orbit around the outside. You get this information from your periodic table. If you look at an element, so for instance, helium is 2 and 4. The 2 tells me that it's protons, 2 protons. The 4 is the total mass of this nucleus. Well, if 2 of them are protons, that means there's 2 leftovers, there's 2 neutrons. And then also, protons are positive, neutrons are neutral, electrons are negative. The number of protons you have will be the number of electrons you have. So in this case, I've got 2 protons, so I'll have 2 electrons, and they have a negative charge. This is a very, very common exam question where they ask you to fill in the gaps. Do you know what the mass is? Well, a proton is 1, a neutron is 1, electron, very small. It's like near enough 0. The relative charge of a proton is positive 1, neutron is 0 because it hasn't got a charge, electron minus 1. When you're looking at electron configuration, you always remember to fill it up to 2 in the first shell and then up to 8 in the second shell. So once it's full, you then have to go on to a new shell. Okay, isotopes. They generally just, if they do ask you a question, they generally just ask, what does isotopes mean? So if you look, this is an isotope here of hydrogen. They've all got the same proton number. They've still got 1 proton. However, if you look, this one has got 1 mass, this is 2 mass, this is 3 mass. That means this has got 1 proton and no neutrons. This one's got 1 proton, 1 neutron, 1 proton, 2 neutrons. So an isotope is an element that has the same number of protons but different number of neutrons. So usually they give you a diagram as well with isotopes. So just say what you see, and don't forget the key is on the periodic table on the back of your exam paper. Ions, on the other hand, if you see the word ion anywhere, it just means charged particles. So, for instance, sodium here is charged with a positive, which means it's lost 1 negative electron. Fluorine, which is negative, has gained a negative electron. If you see that word ion anywhere, it's to do with charged particles. So, ion is a charged particles. Ionisation is the process of charging a particle. Ionic equations are equations with charged particles in them, just like it's got there. Okay, if we have a look then at the development of the periodic table. So 2 people you need to talk about here. First of all, John Newlands, he tried to come up with a table to start with, but at the time we only knew about 63 different elements, and he really struggled to put them into any kind of pattern because he tried to use the atomic weight and it didn't work. We know that the proton numbers are important, and we also know about the actual properties of each of the materials, the elements, which is why they're put in the order they are. Dmitry Mendeleev, he realised we did not know all of the elements, and when he put together his periodic table where he put chemicals into groups with similar features, he actually left gaps because he knew that we hadn't found them all. And I think that must have been a really exciting time for chemistry, because chemists and, well, everybody would have been running around all over the world trying to find the chemicals that went into those gaps. And a lot of them were very successful. The last part of this video is looking at the different groups, looking at group 1, group 7 and group 0. So you need to make sure you know about the properties. So first of all, group 1 are alkali metals. If I put that metal into water, it will turn the water purple with pH indicator because it's made it alkali. It forms a hydroxide with the water. It is more reactive the further down you go on the periodic table. So it's more reactive further down you go. Whereas I always think about a big U shape, because group 7 is more reactive the further you go up. So down group 1, up group 7. It's stored in oil to stop the metal reacting with any air or water. The oil acts as a barrier. It has 1 electron in its outer shell. They have low melting and boiling points. We know that because of how reactive they are. It's really fast reaction, and it decreases down the group. Halogens, group 7, are non-metals. They have 7 electrons in their outer shell. They are more reactive the further you go up. So at the top here, fluorine, he's the biggest bully out of the lot, and he will always take over from anything below. So if I've got sodium chloride and I put in fluorine, the fluorine will push chloride out the way and will take over. So it becomes sodium fluoride plus chlorine. Don't forget it becomes an ide when it joins on to another chemical. They are diatomic. They travel round in pairs. So it'll always be F2, Cl2, I2. And like I say, more reactive will displace or push the other one out the way. And we'll look at displacement reactions in a little bit more detail in a minute. And the last group to look at is this one here over on the right hand side, called group 0. They are called the noble gases. They do not react with anything pretty much because they have got full outer shells. So some people call it group 8, some people call it group 0 because their outer shell is full. Okay, so that is the mind map for part 1. Please go on to the video for part 2. There are 4 videos for the whole of the chemistry paper 1. Thank you for listening.